Welcome to the CSC Colloquium. Today we are very excited to welcome Dr. Rafe Levine. He is a prolific open source hacker. He has a PhD from Berkeley on the topic of interactive curve editing. And currently his day job is working on mostly GPU font rendering at Google. And today he's going to be telling us about wanting a good parallel computer. So let's give a warm welcome to Rafe. Apparently folks cannot hear Rafe on Zoom. So what if I just hand you, well, let's see if we can fix it quickly. And if not, then I'll hand you this mic.
Oh, well, the mute was on. Okay. Oh, now I hear my voice. Okay, thank you. All right. So who am I? Why am I interested in this topic at all? So I am a research software engineer on the Google Fonts team at Google. And most of my work is on 2D rendering algorithms that run on GPUs, and that is font rendering, but other 2D vector graphics as well, not just fonts. And almost all of the work that I've been doing for the past few years is focused on compute shaders. So historically, GPUs focus on a rasterization pipeline where everything is made into triangles. And from my perspective, the only triangle that I ever see is when people make a Bezier path that has 3 points on it. I've also been spending a non-trivial amount of my time and effort on trying to move WebGPU forward, make WebGPU a better computing platform. And I've been collaborating here who are working on the conformance test suite, including things like memory model, which is very exciting. I've really been developing a love-hate relationship with GPUs. There is lots to love about them. That fundamentally, they have 10 times the throughput as a CPU, and there's lots of different ways to measure that. My favorite way of measuring is throughput per watt. I feel like throughput per dollar and throughput per watt are basically the same, and that's just a really nice objective metric. And it's 10 times better than a CPU. And when you're rendering a lot of stuff, then you really want that. You wouldn't be able to sustain smooth interactive frame rates just doing CPU rendering for a very complex scene. On the other hand, I have been becoming painfully aware of the limitations of GPUs and frustrated by the current state of tools, programming languages, debuggers, et cetera, et cetera. And so this talk is about a vision of how could we do better than GPUs today. So the parallel computing dream, actually, the first massively parallel computer was the Iliac 4, which is as old as I am, I think 1970. But the clearest realization of the dream of massively parallel computers started around in the mid-'80s, 1985, with Connection Machine 1, which really came out of MIT. And this device that you're looking at has 64K nodes. And each node is very weak. It's not a very powerful node, but that's a lot, even by today's standards. Like a high-end GPU is typically 16K cores. And so a lot of the literature, a lot of the algorithms that we still use today come from this era where they started to realize in order to get high performance computing, we need to have a lot more cores. We can't just have a single. And so when you're trying to map an algorithm to a highly parallel computer, in my mind, I'm kind of dividing it into 3 categories. So the easiest is embarrassingly parallel. And this is sort of a solve. That you look at the problem and it's obvious where the parallelism is. You don't have to do a lot of thinking, a lot of analysis to figure where is the parallelism that I can exploit. And then when you run the thread, so you parallel program, so that means that there's lots of threads and each thread is executing independently. And you don't have to do a lot of coordination. Maybe there's something at the end where you report your result and you gather the results together. But for the most part, you're just doing your computation in your own thread, and you're not really needing to communicate or coordinate or synchronize between the different. And the other thing about embarrassingly parallel problems is that the scheduling of the work is straightforward. A lot of times it's just a grid. Like if you're rendering a lot of pixels, like Shader Toy is a really great example of embarrassing parallelism. What you're looking at here is a mathematical function, a rather complex, like sculpted mathematical function, but a mathematical function that is being evaluated at millions of points, one for each pixel. And actually, t is another parameter of that function. So if you go click on the link, and I hope everybody has access to the slide, you'll be able to see the information in there. So each pixel is just this rather complex mathematical function. You can see the sort of mathematics in it, that the spiral is a logarithmic spiral. So that's in there in the code. Then there's a middle category that I'm calling, this is not standard, embarrassingly parallel is a standard term, but these other two are kind of terms that I made up, invitingly parallel. The parallelism is there. It's not that hard to figure out where the parallelism is. There is going to be some coordination between the threads. You don't have them independently doing their own computation. And the scheduling of the work may be a little bit more dynamic. You probably aren't just saying, here's a big block of data, run all these threads. You might have to look at the work that you're computing in order to figure out how to schedule the different pieces. And then there's this third category, which I am calling humbling parallelism, because trying to really implement these algorithms for real on real hardware in real systems is a humbling experience. So the parallelism is there. And in a lot of cases, finding out where that parallelism is that you can exploit is a research paper, a lot of which goes back, like research on things like parsing, the kind of classic science algorithms. A lot of that was done in the 80s and 90s, but it continues. It's continuing to be academic research to say, how do you map this problem, which looks kind of sequential, into a parallel computer? Then there is a lot of coordination between the threads. You really have to, the contribution of an individual thread to the whole problem is not obvious. You have to do a lot of communication. And then this is really the part where GPUs today struggle, is that the scheduling of the work may be highly dynamic. You may have no idea that you need to run a particular block of work until you see that structure in the problem. As I say, the first category is embarrassingly parallel. This is not that hard to understand. And so I showed you this shader toy screenshot, and there's a bunch of things that fall into this category. A lot of the core of 3D graphics, the evaluation of vertex and fragment shaders, is basically embarrassingly parallel. Each vertex is independent. Each fragment, which is sort of a pixel shader, is essentially independent of all the others that are running. Computing Bitcoin hashes, which I don't consider a particularly interesting problem, but it's certainly embarrassingly parallel. There's some other fun ones, like if you're doing number field algorithms for factoring primes and so on and so forth, then the sieving step is embarrassingly parallel. And then there's a lot of other things, like if you're doing database search of something like a genetics database, then you could really say, I'm just going to do this match completely in parallel across all the rows in my database. So it's important. Like you want embarrassingly parallel, but this isn't where the juice is in terms of interesting academic research. So in this middle category, invitingly parallel, there's a lot of examples that come to mind, and some of which are extremely important. Matrix multiplication, obviously. Image convolution is very similar to matrix multiplication. In both cases, you're just doing dot products, fast Fourier transform. A little bit more complex structure. It has that logarithmic like chart. And there's a lot of tasks in 3D graphics that fall into this invitingly parallel category. Like if you're procedurally generating geometry, you've got a hill that's got brass on it, then you can say, you generate the blades of brass, and then each blade of brass generates some triangles. And so that's obviously not embarrassingly parallel, because as you zoom in and out, it's going to depend on the level of detail. It's not that hard to coordinate. I would also put vanilla ordinary prefix sum into the invitingly parallel example. So the core key invitingly parallel problem is matrix. And again, looking at this, you can obviously see where the parallelism is. There's parallelism not just on I and J, but also in K, because this is a reduction. So you can do that reduction in a tree, take pairs, and so it's log n. And so you can do this problem in log n steps on a computer with n cubed over log n processors. And this is probably like a significant fraction of all computer cycles is computing this, because this is the part of machine learning. And you look at something like a large language model, and a vanilla large language model is like 500 lines of Python on top of a very fast, very high performance matrix multiplication. So this is soaking up everybody's attention. But I am interested in more challenging problems. I like these humbling parallels. And there's a lot of good literature. There's a lot of really good work that's been done on this. I did a deep dive earlier this year on sorting, and I'm planning to use that as part of my rendering algorithms. I'm happy to talk to people afterwards if you want to do a little kind of the structure of this talk is it's going to cover a lot of highlights. I'm not going to go super deep into any one of these topics. Even matrix multiplication is interesting if you're trying to be sparse. It turns out when you have these matrices, a lot of entries are 0. And so actually going in and multiplying all those zeros is wasting energy. And so maybe you want to do it in the sparse blocks. And now you've got this structure. Now you don't know that kind of difficulty in scheduling work. You don't know what work you need to schedule until you look at which blocks are sparse. Parsing, that's a fun one. We actually do parsing. We actually build a tree out of, when we do clipping and blending, there's a begin clip and an end clip, and we actually parse that tree on the GPU. Data compression, also very important. When we get into SAT solving, this is actually out of my wheelhouse, but I just throw it in there because it's a really classic computer science problem, and there is parallelism, and it's definitely an advanced research topic. It's not obvious. How do you run SAT solving on it? Then, as I say, my main work is doing 2D graphics rendering, and I have found that there are a lot of these humbling parallel problems in the rendering of 2D graphics. So I'll give you a quick demo. I'm not going to spend a lot of time on this because I have a lot of stuff that I want to go through. But this is the renderer that we built, and it is running, in this particular case, in a web browser. So this is running on web GPU. You can just go to that URL yourself and run it on your own computer. It is running, it's a pipeline of compute shaders. I'm going to talk about it a little bit more. To show you some of the stuff. So this is new work that we have all of the stroke to curve, stroke to fill expansion. This is being evaluated on the GPU now, which is exciting and new. And you can see, so this one is showing some of the other foundation for the work that we have. Animated variable font rendering. That's really a major motivation of why I'm doing this. And there's some other things. These are kind of test images, engineering test images. They show you a lot of what's going on. So this is the, whoops, zoomed too far out. So you can see the FPS counter is starting to grade a little bit, but this is a pretty complex scene. This is not that easy. I'll show you another one that I have lined up. It's a good demo. And so this is a map of Paris. So this one I'm not running in I could be running in the browser, but I'm not. I'm running it natively, and you can see that it's sustaining 100. Actually, I turned VSync off. It's doing 150 frames a second on this map of Paris, which has, you can zoom and see the vectors. This particular image has 1 million path segments on it. So it's really high performance. You need the GPU to obtain this level of performance. So a lot of these humbling parallelism problems, there is kind of a key that unlocks a lot of them, which is prefix sum or scan in the generalized case. And it's kind of a magical algorithm that it allows this stateful interaction. You can have one thing one element that the effect of that continues over the entire span of the problem, and it has this beautiful log-n algorithm. In a lot of applications, not just the ones that I'm doing, but like, for example, if you're doing sorting, then one of the faster sorting algorithms is basically built on top of a prefix sum, a scan of the digit histograms for radix sort. So my most recent work, so this is a paper that is in production, in preparation, is stroke expansion. So you take an outline on the left, which is font, and it's got cubic Bezier curves on it, and you break it down into lines so you can render it. And this is a humbling problem, because how do you make sure that outline on the right is watertight? You've got to deal with the joins between the different segments. You've got to evaluate the curvature to make sure that the spacing of the sample points is right, that you don't want to be too tight, otherwise it's too slow to render, you generate too many segments, and if it's too loose, then you don't render it accurately. So that's a paper in progress. There's a link to that. We're working in public. And the core, again, is prefix. So I want to go a little bit into hardware. I want to go a little bit deeper. That why is the GPU 10 times more power, more throughput per watt? And one way of looking at that is, what is the ratio of the real work, the multiply? A lot of the work is multiply adds. So what is the ratio of the real work that's being done to all of the overhead, all of the coordination and shuffling and instruction decoding, and so on and so forth? And on a CPU, it's almost 1%. And this image that I've done, this is a kind of it's actually representing power, like where the power budget is going, but I've drawn it so that it looks like a chip layout. It's strongly inspired by a chip layout, but it is actually to scale on this particular measurement. And it's a little bit of an older chip because I was working from public data that was easier to find, this ISSCC paper. But this is actually to scale of the amount of power that it takes to do a 32-bit floating point multiply divided by the flops on this particular Intel CPU. And so you've got a modern CPU is doing a tremendous amount of work, a lot of complexity, a lot of sophistication in order to give you the illusion of single-threaded execution. So there's all this out of order scheduling and register renaming to get you need to extract some of the parallelism at the instruction level. And then it's got things like branch prediction, because if you do mispredict a branch, then the pipeline stalls for a very, very, very long time. And so you want to predict those branches, so you don't do that. And then a huge amount of the chip area, power, complexity is the memory hierarchy. Because you're not just sitting there doing multiplies, you're getting that data from someone, reading the input, then you're doing the multiply, and then you're writing that result back into memory somewhere. And you want that to be in L1 cache, because there's no way, if you had to write everything to main memory, you just would not have the bandwidth for it. I strongly recommend this particular part of the talk is inspired by a talk from Bill Daly late last year, Trends in Deep Learning Hardware, where he really goes into a lot more detail, especially the relative power consumption for things like multiplying versus reading a word from static RAM or going to RAM or something. So when we go from a CPU to a GPU, it's actually not that different. It's kind of the same story, but tuned differently. So the main thing is that we have huge vectors, and CPUs have vectors too. There's this thing called SIMD, single instruction multiple data, and that helps for throughput. That throughput number that I was giving before is assuming that you're exploiting SIMD. But on a GPU, it's all SIMD. It's a very wide SIMD. It's usually 32 lanes of SIMD. And that means that you can amortize that cost of the instruction decoding and so on and so forth over a lot more real work. You're doing a lot more actual computation of numbers for each one of those, for all of the scheduling work that you're doing. And there's other trade-offs that you're making. You're not focused on single-threaded performance. You're not focused on latency, so you can tune the knobs, focus on throughput, make each individual core a little simpler, a little lower performance, so you can fit more of them on the chip. And I think the other thing that makes a GPU different than just a CPU with lots of SIMD is that you've got this concept of workgroup. You've got this granularity of computation, which is explicitly exposed to the programmer, that says it's typically around 256 or 1024 threads. And within a workgroup, you've got synchronization primitives and communication primitives that are very cheap. It's like basically 10 nanoseconds to go from one thread to another within a workgroup. And then to go across workgroups is much more expensive. And having that communication, that coordination, synchronization inside the workgroup allows you because you've got so many work groups that are evaluating in parallel, that allows you a lot of throughput without that going into main memory. So when you start mapping workloads to this hardware, then one of the things that emerges as, I think, a general pattern is that these workloads are graphs. You've got stages, and each stage is doing some piece of the problem, some part of the computation, and then flowing those in a sort of a one-directional edge over a graph to another one. So this is I'm not going to go into lots of detail. If you are interested, there's a Rust Lab talk from November, and I go into a lot more detail there. But this is a general picture of the different stages, the different graph stages that we're doing in Velo. And one of the things to note while we're looking at this is that there's some joining, that it isn't just a straight pipeline. And in our particular case, the main thing that we care about is bounding boxes, because we need to know that bounding box before we can schedule the, computational pointing numbers and so on and so forth that goes into that bounding box. So there's this kind of forking where you've got, you're looking at some of the problem, and then you're computing those bounding boxes, and then you're using those bounding boxes to join them to the computation. So when you map this onto a GPU, today, then you're using compute shaders. You also have a possibility of using CUDA, which is a compute-only API. But it's actually not that different. The dispatch structure is pretty similar between CUDA and compute shaders. And the way this works is that you do the dispatch of the compute shader itself as a 3D grid. And a lot of times you're only using one. To draw it as 3D looks cooler. And so you've got the inputs and buffers, and those are just ordinary, that's just RAM, that's just, there's nothing special going on there. You've got the inputs and buffers, and then you dispatch this compute shader, you give it a grid, X, Y, Z, and you say run all the threads in there, essentially in parallel. It's all scheduled by the GPU hardware. And those threads are going to write their output other buffers. The problem is, this is where we get into memory model stuff, as a specialization here, that if you write into memory and then you read it, how do you know that you're not reading a stale cache? The hardware does not have memory coherency. That's actually part of the magic of what makes it higher throughput at lower cost, that you don't have the cost of managing coherence of the memory. So what you have to do instead is that you write your output, then you stop all of the work. You have to, if there's a straggler, if there's one of those work groups that's taking a little bit longer than everybody else, then you wait for that while all the other work groups are sitting idle. That finishes its work. You stop the work, wait for idle, you flush the caches. So now the memory contains the actual output of what those compute shaders computed. And then you start the next one. Now, depending on the structure of the work, that might be fine. For a lot of AI type workloads, that's fine, because these compute shaders, they may be going for tens, hundreds of milliseconds. And so that cost of the pipeline barrier, which is in the handful of microseconds category, doesn't really count very much. But if you're doing more humbling parallelism type problems, you might have a compute shader stage that only is going to take a microsecond. And so to wait a few microseconds for that pipeline barrier may really be slowing you down. That's one of the problems. The other problem with this picture is when you've got these intermediate buffers, how big are they? And this is actually turning out to be one of the biggest problems in practice for running this renderer, because you have to allocate that ahead of time on the CPU without knowledge, like, zooming in and out. When you zoom in, that's changing the number of tiles that it has to generate and store in these buffers. And so you don't get to just reallocate in the middle of a compute shader dispatch. And so when I say I want a good parallel computer, then give me one where I can do reallocate in the middle of a compute shader dispatch, and that would go a long way. But I think it's indicating a deeper and more fundamental problem. And when you've got a graph, it really doesn't need, you don't need to have a buffer that has the entire problem. You do that because the pipeline barrier. But if you could really run these in parallel, you'd be getting a lot of things. It's kind of ironic. This is a highly sequential picture at this granularity. At the dispatch granularity, you're exploiting no parallelism, even if the underlying problem has a lot of parallelism. Which it does. So compute shaders are kind of exploding in popularity. You look at a modern game, over 50% of the GPU time is actually being spent in compute shaders instead of the rasterization pipeline. There's a great analysis by Chips and Cheese. If you follow that link, it analyzes Starfield and kind of breaks down what it's actually doing. And so there's a lot of stuff that you can do in compute shaders that is really cool. You can generate procedural geometry. You can do your image filters, your blue, your blurs, your all those filter effects that are amazing. There's a lot of neural techniques. People are doing neural upsampling. There's neural rendering. Obviously, you want to do your physics simulation, your water, et cetera, et cetera. The kind of core computer graphics use of these things is culling. A lot of the triangles you don't need to render, so why don't you recognize those early in compute before you send them down? And then there's a lot of alternative rendering techniques that are not based on triangles. So there's distance fields, there's Gaussian splats, and those all work really well in. And then I really recommend this talk if you are interested in this topic. But the Unreal Engine 5 has this renderer called Nanite. It is very sophisticated. It uses a lot of advanced computer science algorithms and data structures. It is traversing a DAG in parallel. So it really represents a level up in terms of the sophistication of the algorithm that the GPU is running. And that's in production. That's in. So the computer graphics world, I think, has recognized this. I mean, among other things, there's this Gramps paper from, I think, 2009. And the link is on the next slide. And that's realized. That's being realized in production now. So there's this relatively new work. The draft came out late last year, and it's actually shipping now in D3D12 work graphs. And the idea is that you take that graph structure, which is common to a lot of problems, and you map that to work groups that are going to get dispatched by the GPU. So I'm not going to go into all the detail. This is kind of a picture to evoke why you would do this. It shows, the recursive nature, and kind of gives you a picture. And then at the end of this, the different nodes can be specialized. They can do different things. And at the end of it, they're going to output triangles and graphs without doing those pipeline barriers. So work graphs, again, with the love-hate relationship, that there's good things about them, and there's bad. So the good news is that they actually work. Like they do this dynamic scheduling. They allow you to schedule those work groups in response to the problem that you're actually rendering. The hardware does the load balancing for you, which is one of the big challenges when you're doing compute shader programs. And you can have any graph structure you like. It kind of builds on work called mesh shaders, which is a few years old. And you can think of a mesh shader as just being a graph that has two nodes, and the roles of those two nodes. One is the amplification shader, which generates your grass blades, and the other is the mesh shader, which creates the triangles. And so it generalizes that. And also, when you have those edges are modeled as queues. And so you don't need a buffer to store the entire problem. You can stream the data. You don't have to worry about how big it is, how much memory it takes. It can just stream the data. They are, however, limited in terms of the execution model. And for me, in 2D graphics, ordering is really important. When you have that tiger, the whiskers need to be ordered after, above the base object. When you're doing 3D graphics, you can get away a lot of times without having ordering guarantees. That you use the Z buffer to just decide, and increasingly, 3D graphics is relying on that instead of the ordering guarantees by the hardware, because it's expensive for the hardware to provide an ordering guarantee. These things are being launched, and they'll land in. They also do not support joins, and they are very aware that this is a problem, and they're working. There's a very limited capability called Finnish cross-group sharing, which should give you some idea of the complexity of all of this, just that name. And another limitation is that as you're moving items along those edges, those have to be fixed size. So I think the idea of work graphs was really set out in a very clear and compelling way in this paper from 2009, and it is being realized. And I think that leads us to, I'm going to propose a number of research questions, which I feel hopefully the people in this room are equipped to address. What humbling problems are suited to this new execution model that we now have the hardware to run? And I have a partial answer. I think that you should treat the order, when you have an ordering guarantee, I think you should run the problem unordered and then follow it up with a sort. And I feel like for one of the problems that I'm solving, I think I can do that. But I think this is a more general problem. When you look at that list of humbling problems, humbling parallelism problems, how many of them, now that we have work graphs, how many of them are going to work better with work graphs of dispatch than compute shader dispatch? So when we're looking at like the hardware and the different possibilities versus what do we have today, one of the most interesting chapters in the story that I think of Intel Larrabee as like a alternative universe that we could have had slipped away. So it was a really bold approach to GPUs. That it's fundamentally a general purpose processor. It's x86. You can run Linux on it. But it has a lot of cores, a lot more than usual. It's kind of tuned so that it's more cores with less performance on each core. And it has much wider SIMD units. It has 16 wide. And that later became AVX 512, but that has taken a very long time to land because it's too powerful. But it is landing. And then it has a small number of CISC instructions, complex instructions for doing texture lookup, because there are some things that you do want accelerated hardware. But most of the graphics, most of the traditional, like the Z buffering and the clipping and the blending and all these things that you have dedicated fixed function hardware for, it's just software. Ultimately, it failed. And I think that is a tragedy, because if it hadn't failed, if it had succeeded, then you would be looking at that capability of scheduling very dynamically, and you'd be thinking, how can I map advanced applications to this where I'm not limited by the execution model of a typical GPU? But those applications did not materialize. There's an excellent blog. There's a really good SIGGRAPH paper that sets out the vision, and you read that paper. Yes, please build this. And then there's a blog from Tom Forsyth from about, I think, 8 years ago. That's a retrospective. Kind of goes over the failure, but also the ways in which it succeeded and inspired future generations. And I think there's more inspiration to be had. I think this model where you've got a real computer, a general purpose computer that's programmable, that is highly parallel, is something that still has to be. So moving forward in time, another model hardware that may represent an alternative vision, maybe a better vision, is the Vortex GPU. This is academic work out of Georgia Tech. And it really, to me, resembles the Larrabee, only instead of x86, now it's RISC-V. And so it's a multi-core, it's got vector units, and it's got 6 additional instructions that kind of bring in the GPU world, the ability to spawn waves, splitting and joining on predicates, predicated execution. That's another detail that I've chosen not to go into in great detail in this talk, but it is central to use. And it does texture lookup, just like Larrabee did. And they built a lot of software. They actually can run OpenCL, OpenGL, and Vulkan code. Benchmark, see how it runs. It's realized on a high-end FPGA board. I think that board costs about $5,000, $1,000. And it is easily beat by the cell phone in your pocket. But if you want to do research on it, it's great. And they have a great project page. There's a lot of papers. The software is open source. And so I think this is a really interesting direction. I think, again, this is a research question that a lot of the work in this space is being driven by AI, but AI has been constrained by what GPUs give you. What if you had a good parallel computer, an architecture that supported this more fine-grained scheduling of work, this more dynamic load balancing? Are there AI algorithms that you could run? And I think, again, phrasing this as a question, I have a hypothesis that sparsity is going to be the main thing that you will be able to study, but I think it's an open-ended question. So possibly the most exciting direction is AI accelerators. So in other words, things that are not being built primarily to run graphics workloads, but to run AI workloads. And there's a Canadian company called TensorTorrent. They're building hardware that I have, and I intend to experiment with this, but I haven't had time. So if there's anybody here who would really be interested in doing some experiments and exploration, then I will be happy to loan you this hardware. This hardware is a grid of RISC-V cores. And the grid nature, it's really, I think, more than many computers, it's going with the grain of the physics. It's not trying to abstract the physics away. These are laid out in a 2D grid on a chip. Each node in this grid has an XY coordinate. And when you're programming it, you explicit, I'll get into it a little bit in the next slide, but that's not hidden from you. It isn't, there's not some scheduler that's deciding which core runs your particular piece of work and that's abstracted away from you. It's part of the hardware. So most of the interior of the chip is these 10-6 cores, and then kind of at the edge, you've got interfaces to DRAM. That's low power, inexpensive DRAM, which is one of the big differences, that a GPU is so hungry for bandwidth that the DRAM on the GPU is really the most expensive part. That's why you can't buy a consumer card that has more than like 16 gigs of RAM on it. And on the other side, you have a network and host interface. So you can go over networks to other ones of these, or PCIe or host. And on the chip, internal to the chip, kind of connecting these cores together, you've got a torus network. And a lot of the design of the chip is geared towards making that work. Each one of those 10-6 cores looks like this. You've got 5 RISC-V cores that have very specific roles. So 2 of them are dedicated to the network, and they're connected directly to network routers, which are on this torus network on the chip. And then the ones in the middle are connected to a matrix and vector engine, so something that is capable of doing a lot of multiply adds in parallel. And everything inside the core is stitched together with 1 megabyte of static RAM. And it's multi-ported, but the number of ports on it is not extreme. It's like enough for all of these pieces to connect to. And so when you're getting data in and out on the network, that's going into static RAM. And when you're doing the matrix multiplications or other math, that's going into static RAM. And the model is that you're programming this explicitly, that you're saying, send the data over the network to the XY coordinate of the core that's going to do the computation. And then that receives it, it does the computation, puts it back on the network. So a lot of the stuff that GPUs do for latency hiding and so on and so forth goes away. A lot of there's no cache. The memory hierarchy is very simple. It's like, get your data in, get it into static RAM, which has very low latency, do your math, get it out. So, and so there's I really recommend this talk from Jim Keller from last year. I think it presents the case for this and why you're going to be able to do more work with less energy in a compelling way. Then we get into this question. If you have this hardware, whether it's a GPU, whether it's NVIDIA style with CUDA, or whether it's maybe some of this new AI accelerator, how do you program these things? And this is where the big challenge is. This is, I think, even if a good parallel computer fell from the skies, we still would have a great deal of difficulty using it, because how do you write programs? And in putting these slides together, I realized that there's like 3 or 4 competing visions that are surprisingly different. It isn't like there's the same concepts that are just sort of remixed. These are very different visions about how you program the computer. And that, in turn, is affecting how we build these computers. In the CUDA vision, which is extremely compelling, every thread runs a C++ program. And one of the reasons this is so compelling is we know how to write C++ programs. We don't have to invent a new language. We can add a few intrinsics to do your communication between threads and so on and so forth, but write most of the thing in this language that we already know how to do. The communication between the threads is through memory, because that's how you do communication between threads in C++. You write into some memory location, you have some synchronization, and then some other thread reads that memory location. And that is one of the reasons why these things are so power hungry. You have to move that data into memory. Huge amount of effort. It's a cooperative effort between the hardware. The hardware is doing a lot. The compiler is also doing a lot to analyze your program, figure out which parts are uniform, do the predication of the execution. Though again, that's moving into hardware too, especially in Volta, there's independent thread scheduling. That gives you a much stronger forward progress here. If you've got two threads in the same subgroup that are contending for the same lock, one will win, and then the other thread in the same subgroup will wait for that to release it and then get it. If you did this on a compute shader, then you just hit a deadlock. Of course, that means no forward progress. So you can really think of CUDA as practical because it solves the problem of what programming language do we use and do people know how to program this model? And it works. It's good. Everybody in AI research uses CUDA. Then there's compute shaders, which I think are maybe downstream, maybe in, like aspiring to being CUDA, but falling short in some important. And so you're not running C or C++. You're running a language that you wish was as powerful and as nice and as friendly as C. It doesn't have recursion, doesn't have function pointers, regular pointers. There are kind of pointers, but I mean, if you're used to programming them in C, you wish for the execution model is very weak. You don't get progress guarantees. Your memory model is tricky. It's adapted the C++ memory model. I feel ultimately, I go so far as to say that GPUs adopting the C++ memory model is a mistake, but maybe around another day. So there's a really interesting project called VCC, which does attempt to compile C to Vulkan compute shaders. And I think that this project is interesting largely for the places where that turns out to be really hard and where you don't get so worth looking into. And in general, shader languages suck. They're bad. You don't have, there's no way to express abstraction. So there's a new language coming down the pike from NVIDIA that has like Haskell type classes or Rust traits in it. Like you can express abstraction. It's still recognizably, it's not like a completely new model. It's your compute shader, model, but it's a pretty nice program. So I think this is going to. And then there's also WebGPU, which solves a lot of the portability problems. That this is something that is being standardized, is being documented. There's lots of good implementations. It's being tested. Again, work being done here is contributing to that. And so I think my personal feeling is that you're going to see compute shaders like take root even more deeply for graphics workloads, but because of these limitations, at this point, like I was hopeful. I thought maybe you'd see computer shaders used more, and you'll probably see people run WebGPU because that's the way to target the web. But I think that for the most part, compute shaders are going to be used for. And then there's the PyTorch. So when you're doing AI, you really want all of the details to be abstract. And so the way you do this is you write your program in Python, and as the program runs, it generates this graph. And then there's a compiler that takes that graph and lowers it into the GPU. And that's doing a lot of really smart optimizations. And when you're an AI researcher, you don't want to care about any of this. And it sort of targets compute shaders, but it really targets. So the good news is it's easy to use. Like, you can use this. It works well. But when you do these humbling parallelism problems, you just can't express it. It's like. So then there's the model. I think this is one of the really cool things about this hardware, that they also have a programming model where you're just writing programs that run on those individual cores. And you're being explicit. So it's simpler, but harder. You have to decide when that data gets into RAM, which XY node you send it to over the network. And there's a small library for those network and math functions, and then there's intrinsics for the math unit. But one of the reasons why I think this is really excellent for academic research is that their entire tool chain is open source. Just click that link, and it's right there. And I actually read it, which if I said I read CUDA, the CUDA source, that would be possible. But it's just too complicated. But it's pretty simple. Actually, it's not too hard to get your head around. So there's a ton of work in making these things run large language models. But to what extent can you run other workloads? I think that's an open research question. I think there's a lot of things that you might want to look at in particular, starting with prefix sum, because that's the foundation of so much work you do. Sorting, can you do sorting on this? Problem that I think is really interesting is, can you do rasterization on it? Because then you can measure how many pixels per joule. And if that beats a GPU, then the game has been changed. And are there other ways? Open question. And are we constrained on time? Okay. I will go slightly faster because I do want Q&A. So I won't go through every point on these slides, but you know, this really, to me, speaks to different visions of what we might get. And there's dystopian visions, and then trust me, there will be a good vision as well. So the dystopian vision that's AI flavored is that the hardware becomes more and more specialized to just doing tensor multiplication and nothing else. And also with a focus on lower precision, because it turns out that you really don't need 30-qubit floats. You don't even need 16. It's unclear that you need 8. And so in this model, you're just not going to do programmability. You're only going to be focused on those matrix multiplications. You're only going to be writing programs in PyTorch. And you're basically never going to express these more interesting parallel problems. And you're going to get more and more complexity in the way that that these graphs are lowered into the GPU hardware. The dystopian future that's GPU flavored is that you get these more complex and elaborate execution models like work graphs and mesh shaders and so on and so forth, but they never quite get to the point where you can just write a program or write a parallel program. And one of the problems with GPUs is that they only add complexity. Like you've got this thing called geometry shaders, which don't work. They recommend don't use them. But of course, they're there. And you're going to see more and more hardware that's specialized to ray tracing, to video codec. Video codecs should just be a program that runs on a parallel computer. But no, you've got to have hardware because there's no way to get to that programming capability. And so the hardware is different on every GPU. All GPUs do video encoding, decoding because error, but it's locked away. Of course, then we get into the problem of the toolings. And so maybe we never really get a good shader link. And the other problem is that there's incompatible standards. On Mac, there's Metal. On Windows, there's D3D12. On Linux and Android, there's Vulkan, and they're not compatible with each other. When you try and translate, there are translation layers, but those are leaky. And I also feel like just the complexity of, and the fact that most of these things are underspecified. Vulkan is pretty good. WebGPU is better. These are being specified. But when you look at Metal and D3D12, there's no spec. And so it's inevitable that the implementations will be buggy, slow, and full of security vulnerabilities, which I think is going to be an increasing area of concern. If you've got something this complex, it is riddled with security vulnerabilities, and there's no way to deal with them. And I know Tyler's done some work on that. We're going to see more. There's a future. So what is the alternative vision? Obviously, I would like to see this grid real computers in. And what is going to decide it is, do you get a win in throughput per watt? Are you able to use less power to shuffle that work and organize it by explicitly sending it over a network to SRAM rather than having all of this cache hierarchy and so on and so forth? And in this vision, you actually get to write your own programs and run them on the cores. And it is very challenging to program. I personally would rather program this because it's simpler to understand. I cannot understand the performance model of a GPU. It is too complex for me. And I've been doing this for years. But if you're just running straight line code on a core, but you've got hundreds of them, you can reason about that. You can actually imagine Oh, I'm a little unusual. I think most people are going to want a higher level language that sort of captures that abstraction. And so in the glorious future vision, I can just magic good programming language to existence. And I do think that I think the emergence of these parallel programming languages is gated on having a solid underlying execution model, which I think we do not have. I also think GPUs can get there. I don't think this is too much to ask. That the fundamental problem, like once you dispatch a work group, what happens inside that work group works really well. It's very high performance. You can program it, it works. But getting those launched is the challenge. And that's why we have these different models with work graphs and so on and so forth. So in my vision, it's you write a little teeny program that says, the inputs are ready. I am going to launch this particular work, or I'm going to decide between these particular work groups that I might launch based on load balancing. In order for this vision to really manifest, then we need to have a lower level API because the Vulkan is just too complex. So ideally, you say, here's a program, here's a parallel computer, and I'm going to write Vulkan as a library. I'm just going to, just call into, dispatch render pass with color attachments. And so that way the complexity becomes that, that library can deal with all the compatibility problems. But if you don't want that complexity, then program directly to it. This also needs a good programming. Maybe the same programming language as the other vision. If it's magic, I can magic 2 programming languages or one that serves both needs. So designing a programming language for this hardware is obviously one of the big research questions. There are academic, work, but there's nothing that's really emerging as a solution. So wrap up, well, we do have time for questions. I think a good parallel computer is possible. I think the physics, points the direction. You want to minimize the amount of overhead for the amount of useful work that you have. And I think there's some interesting directions. But the trends in the industry are honestly not looking very good. I think you're going to be seeing more and more specialized stuff that meets, the business needs of AI or the business needs for 3D graphics and doesn't have this beauty of, what I believe is possible of this highly programmable parallel computer. But I do think that academic research, if we start playing with these things, doing experiments, suggesting like, hey, if you build this thing, it would have amazing performance per watt. So, like ideally, I want to inspire people in this room. Like, you are the ones. We're going to do this research if we're going to build this future, and you are the ones who.
All right, let's thank Raf. All right, question time, and I'll pass the mic around.
I have 10 questions, but I'll limit myself to 3. Well, I guess 10 comments, some of them questions. The first one, I think immediately, like the thing to maybe take note of in this is that GPUs have evolved from like the primordial soup of fixed function hardware, right? Like we only got programmable shading in shade trees in '83, right? And then, the silicon graphics machines were just as, we tried to solve embarrassingly parallel better. And then we tried to solve invitingly parallel better. Yep. And now you're like, well, how the hell do we solve the third one? Humblingly parallel. The other comment I have is that you mentioned nanite. Nanite is maybe the bigger news is like nanite is in Fortnite. Like,
yes.
There are billions of machines running tons and tons of the work in compute right now. And Unreal itself, like even outside of nanite, is shifting more and more of their rendering to compute.
That's right. Major trend. I heard a report from GDC that like compute shaders was sort of the theme, even more than that.
I didn't go to GDC, but I talked to someone at Epic who was saying about the same thing. The maybe the third larger thing that I have to comment is that like you mentioned Larrabee. Larrabee is about the same time, and maybe a big missing component in this history is you're like, oh well, Larrabee failed, never came out. We didn't get any Larrabee hardware. We got Cell.
Yep.
Cell is is very similar in that way. Like the
You know, I almost put cell on the slide, and I chose not
of
to
everything.
because I think it's considered a backwater. I think people consider it a mistake because of the difficulty of programming it.
Yeah.
I think if you look at why do
PS3
modern day
developer, right?
GPUs not resemble cell, it's because, you know, that hardware was there, was kind of amazing for its day, but it didn't get exploited because it was too hard to program.
Yeah, I mean, because ask any PS3 developer who tried to write, or anyone porting a non-PS3 game to PS3, like
Yeah.
trying to program for that machine is hard. But the idea of like, we have these not completely dumb cores that are connected to a high speed interchange
Yeah.
is like, is there.
Yeah.
And existed more, I want to say, in Cell. I don't know as much about Laramie, but I know that I've spent tons of time staring at the Cell Wikipedia page. Like, oh, so that's
But
probably myself.
when I do the blog version, one of the things I want from this Q&A is feedback to help me improve the blog version of this talk. So I'll make sure to put cell in there because I agree that is real.
Yeah. So Laramie shipped,
Yeah,
and it became #4 biggest computer in the world at one point.
yeah,
So yeah, if those are not aware, Intel branded it as Xeon Phi when they shipped it. And part of the reason why they fell off the wagon was not so much architecturally, but because the process died, right? As part of the process throws post 2016,
Yeah.
they stopped supporting that lineage. But I mean, yeah, there was a Laramie 1, 2, and 3 as the code names internally. And then, you know, you have your Knife Landing, Knife Falls, etc. as the
yeah.
actual products that you shipped.
It did ship, and so maybe, and that's a major point that you know, that Tom Forsyth's blog makes, that, you know, people. I think it's fair to say that it failed, but he would argue with that, and it did ship. There were people that used it, and I think the other thing, one of the ways in which it succeeded is that I think that GPUs have become more Laramie-like. You look at an AMD GPU, then there are a lot of things that kind of look like Laramie, especially compared with the older fixed.
So you talk about this, you have this new tens torrent machine. Seems really interesting and like a new way of writing parallel programs. And you mentioned on the slides that it should just run a C++ program. I assume that doesn't mean it runs the C++ memory model or something though. Like, how do you see the coordination? Is it like a message passing kind of system? Like,
Yeah.
what is the model that we use to program these and
That's right.
coordinate?
So it is running C++, but it is running embedded C++. And so if you look at the code, they use volatile, which I actually gave them feedback. I'm like, to me, this seems kind of archaic, but it's really running. You really want to think of it as running single cores that are then communicating over a network, so that there is an API that says, send this network packet to this XY coordinate on this other chip. So there's no, like, completely unlike CUDA, where there's this shared memory space that you can write data in one, you know, from one and read it in another thread. That won't happen until you have explicit network.
Yeah. So basically like the way that we're going is that all things should be distributed systems. There's no more shared memory. We're writing everything like a distributed system now.
Yeah. Although, like, that virtualization goes both ways. That there's tons of ways of you know, virtualizing it so that it looks like you've got shared memory. Like, I think that line is getting really blurred. And yeah, absolutely, tens torrent is maybe swimming upstream in them.
Hi. Something that maybe you are not aware, but since we've been talking about Laravel, so the team was on Laravel. Part of it moved to Esperanto, and they have an array of RISC-V cores with vectors. They have tape out. You can get access to the hardware you want.
Yeah,
and even has patches like the intrinsic and all those things that they were not having for graphics. So so in a way, the system, even the team, it moved to another place and they developed it.
I almost put the bullet point up for Esperanto. The reason that I didn't is that their stuff is not open source. So I think it's much less suitable for academic research. But it is absolutely another, you know, instantiation of this grid of RISC-Vs. And I think you're going to see others of those too. Like, I see rumors of Chinese effort. Esperanto, in addition to the Larrabee team, also has Dave Ditzel, who was working on transmeta. And so there's a, early VLIW, another idea that arguably failed. So yeah, there's a lot, like, it's exciting because there's now a economic incentive to solve this problem well, at least for AI. And obviously that's what companies like Nextdoor and investment.
All right, I'm going to ask a totally different question that is not about computer architecture. So a lot of your examples are from this from the graphics or rendering world, and it occurred to me that for a lot of these examples, it seems like there's room for a certain amount of like approximate computing, right? It doesn't necessarily need to be the case that you need to get it exactly right. And I'm wondering if you can comment on that at all, right? Like there's some applications for parallel computing where you really need to get the right answer and you really need determinism, and there are others where good enough is good enough.
Yeah.
And it seems to me like that really should drastically affect the design of these machines. So I was wondering if that's something that you've thought about at all.
It is. I think it's an interesting question. Like it comes out in a couple of different ways. So like if you look at prefix sum, if you can, a lot of times you can solve a problem either with prefix sum or atomics. And if you're doing it with atomics, then the order is completely non-deterministic. If you're doing it with prefix sum, the order is deterministic, assuming that what you're doing is actually associative. And that's true for integer math, but it's false for floating. So already you've got some like non-determinism that's going in no matter how you do it. I personally, like my flavor is do it right, that do the prefix sums, have architectures that actually compute the correct answer. I'm not convinced that there's that much that can be exploited by it being approximate, but it may be. I mean, that is definitely a direction to go.
Other questions? And if folks have questions on Zoom, also please raise your hand.
I can read the chat here, people. Should I read the question off the chat? The question is from Sean Siddons. Do you believe that it's possible that an ideal general purpose parallel computer can beat out workload specialized hardware inefficiency performance in all cases? If not, how do you avoid the dystopian future of specialized hardware? I believe that it can beat it in most cases. Beating it in all cases is impossible because ultimately, as soon as you know everything about the problem that you're running, then you can build more specialized hardware. But if you're talking about doing AI inference, or if you're talking about rendering graphics for a game, then I think that I believe, I hope, maybe it's not, it's more hope than based on hard reality, but it feels to me that a highly programmable computer with intrinsics that are specialized, because you can have intrinsics. You can have an intrinsic that says, do a texture lookup, do a triangle rasterization. And it's just an instruction that flips into the RISC-V stream. So I believe you can build those and get that efficiency, and then have it stitched together in a model that is actually simple and tractable to reason about. I believe.
Hey, thanks for the talk, Rafe. So throughout the talk, we looked at different architecture models and you kind of drew them out in diagrams, and I thought that exploration was really good. One thing, and then I even noticed this at the very end of your slide, you're kind of like, programming language is going to be important. And then we didn't talk about programming languages. So I guess I want to get your view, maybe there's 2 points to this. What your utopian programming language looks like, and then what you think a more kind of grounded, realistic language could look like today.
Okay.
And we did sort of mention like a bit of C++ and stuff like that, but even C++ is can be pretty complicated.
Yeah. So I think I was going to ask, can I come back next year and do a colloquium on what I think my ideal programming language looks like? Because I have done a lot of thought on this. So one thing to mention is I didn't put a bullet point for Rust to GPU. There is an effort to translate Rust to run on GPUs. But ultimately, I think that is problematic. I don't think that you really get the benefit of Rust. And I think you run into the execution model limitations of GPU. So I feel like there's an impedance mismatch there that isn't quite the right answer. In my utopian vision, that I really think about this is layering. You need a lower layer which allows you to express the computation. I talk about the laws of physics. Like if you've got explicit networking, you need to be able to explicitly model, this is the node. I'm going to make decisions in code of how to organize the computation and where to send the data. And you need to be able to say that. And then you need abstraction. You need, because I want to say, I just want to compute this prefix sum of this one. And so you want a library that is your monoid mapper, and you give it the parameters. And then you say, here's the monoid, and here's a couple of tuning parameters about how I want this stuff to be scheduled. And then you build upward from physics. There's another school of thought. There's actually, there are some interesting academic languages, and I think there's things you can learn. So there's the array programming tradition, APL. And there's an incredible talk from Aaron, actually not just a talk, several talks from Aaron Shu, who has built a compiler in an APL fragment. And I feel like arrays are cool because the parallelism is there, and you can do humbling parallel problems in APL. But so that's another thing to look at. And I think the array language tradition is probably going to have a lot of juice in it, especially for machine learning type workloads. It's not hard to see how you could imagine an alternate universe in which APL was the language for machine. And then there's Futhark, which is also really interesting. This is the functional programming tradition. But I think that Futhark wins in terms of being able to express the high level stuff. But I think that Futhark has a hole in it where you're like, I know how I want this to map into work groups. I know how I want to dispatch this. That's really hard to express in Futhark. So I would build up from the lower levels. I think it's a super interesting question.
So you've talked a bit about the difference between compute shaders and how they're more limited than CUDA, but you did not mention what dynamic parallelism, where you can dispatch stuff in CUDA from a thread.
Yeah, I'm aware that it exists, and I haven't got my head around the trade-offs. I don't really understand the performance limitations, but it is probably worth mentioning that CUDA does go beyond the grid and pipeline barrier dispatch model. And it may be that is going to be more powerful for certain classes of programs.
Right. So my question was more about, because with compute shares, you have to copy data to the GPU, do your calculation, copy it back. What I was wondering is, you've talked about the work graph model.
Yeah.
Would you be, obviously this would be a lot more overhead for the programmer to do, like you'd have to think about your execution model, but would you be able to build a system that would generate, I mean, you have looked at dynamic parallelism, so I don't know how well you'll be able to answer this, but would you be able to generate a system that will do graph evaluation and do a somewhat like work graph execution on a GPU, where you have a user library using graph algorithms to do dynamic dispatch of your different graph, subgraph parts?
I think so. I think that's kind of the research area. I just want to clarify just one point, which is this copying up and copying back. If you look at Velo, that's a really, like one of the goals of Velo is to minimize that as much as possible. So you do the smallest amount of work to encode the scene into this kind of binary SVG encoding. It represents the scene that you're trying to draw, not breaking it down into primitives like you would usually do in GPU programming. Once that gets uploaded, even though you've got these pipeline barriers between the stages, you're not copying those intermediate results up and down. So you are doing kind of, in the game world, it's called GPU-driven rendering. That you are doing GPU-driven rendering, and I think you are going to see more of that with compute shaders as they get more powerful, with work graphs as you get these other execution models. And it's very likely, if you've got the dynamic graph invocation or whatever that's called in CUDA, that also can support the GPU-driven work. But having looked at that, I get the feeling that it's yet another complex but not fully satisfying execution model. Like, it still looks like you have to have pipeline barriers in place. It's just you get to dispatch it from a compute shader rather than having the CPU have to do everything from a command buffer.
As far as I know, the dynamic dispatch isn't available in compute shares at this time. It's only available from CUDA though.
That's correct.
Okay.
There is in Metal, there is an indirect command execution that is a little bit like dynamic indication, but not quite the same.
Okay.
So it's not portable, but it's starting to show up.
All right. It is just about 12:15, so let's thank Rafe once again.